Look around you, at the desk, the wall, the air you breathe. Every atom, every molecule seems solid, separate, distinct. And look up to the vast, star-strewn canvas of the night sky with galaxies stretching billions of light years away. It all feels so immense, so disconnected. Yet, what if everything we see, from the smallest grain of sand to the most distant quasar, is woven together by invisible threads? Threads that bind particles across impossible distances, that build consciousness from mere chemistry, that link the violent birth of stars to the intricate dance of Danae. This is a journey into the heart of that cosmic tapestry. We begin not with the grand structures, but with the fundamental whispers of reality itself, the realm of particles so small, they defy our everyday intuition. Here, in the subatomic world, the rules of physics seem to bend, revealing a universe far stranger and more intimately connected than we could have imagined. Consider the phenomenon known as quantum entanglement. It's a bizarre link that can form between particles like two electrons or photons. Once entangled, they become fundamentally linked, sharing a common fate, regardless of the distance separating them. If you measure a property of one entangled particle, say, its spin, the outcome instantaneously influences the state of the other particle, even if it's on the other side of the universe. Albert Einstein himself famously described this as spooky action at a distance, struggling to reconcile it with the speed limit imposed by light. Yet, countless experiments have confirmed this eerie connection. It suggests that at the very bedrock of existence, particles are not isolated points, but part of a shared interconnected reality. Our current best map of these fundamental building blocks and the forces that govern them is called the Standard Model of Particle Physics. It describes the cast of characters, quarks, leptons, bosons, and how they interact via forces like electromagnetism, the strong nuclear force, and the weak nuclear force. It an incredibly successful framework, tested and proven through decades of experiments, including those at massive particle accelerators. It tells us what the fundamental pieces are, but it doesn't fully explain why they behave in such strange, entangled ways, or how these fundamental pieces give rise to the staggering complexity we observe. That leap from simple rules and particles to intricate structures in life is one of the universe's deepest mysteries and most beautiful phenomena. The process of emergence. All hydrogen and oxygen atoms, following the rules of the Standard Model and the laws of chemistry, can combine and interact in billions of ways to form water or complex organic molecules. It's how those molecules interacting over vast spans of time can give rise to the first self-replicating structures, eventually leading to the astonishing complexity of a living cell, a forest, a brain, or even consciousness itself. Physics gives rise to chemistry. Chemistry gives rise to biology. And biology gives rise to thought and experience. Each layer emerges from the one below, following new rules and exhibiting entirely new properties that couldn't be predicted by simply looking at the constituent parts in isolation. For centuries, brilliant minds have grappled with these connections, seeking a unified understanding of reality. Thinkers like Stephen Hawking dedicated their lives to probing the extreme edges of the cosmos and the very fabric of space-time, pushing the boundaries of our knowledge and revealing ever deeper layers of interconnectedness, from the quantum foam to the curvature of the universe itself. This is the quest at the heart of cosmic threads. To pull at these connections, to understand how the spooky links of quantum mechanics relate to the formation of galaxies, how the fundamental forces shape everything from atomic bonds to black holes, and how the dance of particles and forces ultimately gives rise to the rich, complex, and vibrant world we inhabit. It's a story not just of isolated discoveries, but of how every piece of the universe seems intricately, profoundly, and sometimes mysteriously connected. To truly grasp these cosmic threads, we must first understand the fundamental knots from which they are woven. What are the universe's most basic ingredients for millennia? Thinkers have sought the irreducible minima, the atoms of the ancient Greeks, the particles of modern physics. Today, our deepest understanding of these fundamental pieces and the rules they follow is encapsulated in what scientists call the Standard Model of particle physics. Think of the Standard Model not just as a list of tiny things, but as a blueprint and a rule book for the universe at its most microscopic level. The blueprint lays out the particles that make up matter, the electrons that orbit atoms, and the quarks that combine to form protons and neutrons, the building blocks of atomic nuclei. There are other, more exotic particles too, like neutrinos, ghost-like entities that pass through us by the trillion every second. But the Standard Model doesn't just name the pieces. Its rulebook describes the fundamental forces that act between them, dictating how they interact, bind, and transform. These forces are the unseen hands that shape everything. Here's the electromagnetic force, the familiar power behind light, electricity, magnetism, and the very bonds that hold atoms together in molecules, the basis of all chemistry. Then there are the nuclear forces, the strong force, incredibly powerful, but acting only over tiny distances, binding quarks within protons and neutrons, and holding the atomic nucleus itself from flying apart. And the weak force, responsible for certain types of radioactive decay, crucial in processes like the nuclear fusion that powers stars. The Standard Model tells us that these forces are mediated by their own partons, photons for electromagnetism, gluons for the strong force, and W and Z bosons for the weak force. It's through the exchange of these force-carrying particles that the fundamental matter particles interact. An electron feels the push or pull of another electron by exchanging photons. Quarks are held tightly by gluons. This framework, though complex, offers an astonishingly successful description of virtually everything we observe, from the glowing of a light bulb powered by electron flow to the incredible energy unleashed in nuclear reactions in the sun. It's a testament to the power of understanding the incredibly small, how the interactions of fundamental particles governed by these forces ultimately give rise to the atoms, molecules, structures, and processes of the macroscopic world. This is where the idea of interconnectedness begins at the very bottom, with the particles and forces that comprise reality itself. While the Standard Model provides this incredibly successful framework, describing the fundamental particles and forces that build the visible universe, it isn't the final word on cosmic interconnectedness. Reality at its most fundamental level holds deeper and stranger secrets. Consider, for instance, the phenomenon of quantum entanglement. It sounds like something pulled from a science fiction novel, a bizarre link between particles that seems to defy our everyday experience of space and time. Imagine two tiny particles, perhaps electrons or photons, created or interacted with in a specific way. According to quantum mechanics, these particles can become entangled. What this means is that they are somehow linked, even if they are later separated by immense distances. The peculiar part is this. If you measure a certain property of one particle, say, its spin or polarity, you instantaneously know the corresponding property of the other particle, no matter how far away it is. If particle A is found to have spin up, particle B, its entangled partner, will instantly be known to have spin down T. Here is no time delay, no signal passing between them. Albert Einstein himself was deeply unsettled by this idea, famously calling it spooky action at a distance. It seemed to violate his principle that nothing can travel faster than light. Yet, decades of increasingly sophisticated experiments have confirmed that entanglement is a very real feature of the quantum world. These particles aren't just pre-joined with opposite states. Their states are correlated in a way that suggests a deeper non-local connection woven into the very fabric of reality. This isn't just an academic curiosity for physicists. Entanglement is the bedrock for potential future technologies like quantum computing and quantum communication, promising levels of processing power and secure data transfer previously unimaginable. It shows us that the universe isn't just a collection of isolated objects interacting through local forces. There are threads of connection at the deepest level, threads that tie distant particles together in an intimate, immediate dance. These entangled links, though invisible to our eyes, are as real as the forces holding atoms together, hinting at a layer of interconnectedness far more profound than we once conceived. If entanglement reveals a universe where distant particles are woven together by unseen threads, then the question becomes, what exactly are these fundamental particles, and how do their intricate connections give rise to the reality we see and touch? Physicists have spent decades seeking the most basic building blocks of matter and the forces that govern their interactions. Their current best answer is encapsulated in what's known as the Standard Model of particle physics. Think of the Standard Model as the universe's fundamental alphabet and grammar. It lists the elementary parters, the quarks that make up protons and neutrons, the leptons like electrons and neutrinos, and the bosons that mediate the fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity, famously, is the elusive missing piece in this standard picture, a puzzle piece we'll explore later. Each particle in the Standard Model has specific parters, mass, charge, spin. They are not little hard spheres, but rather excitations of quantum fields that permeate space-time. And crucially, these particles, these excitations, are capable of exhibiting the bizarre correlations we call entanglement. So the universe isn't just made of stuff, it's made of stuff that is inherently quantum and potentially linked across vast distances. The electromagnetic force, for example, mediated by photons, is what binds electrons to atomic nuclei, forming atoms. The strong force, carried by gluons, holds those nuclei together, overcoming the electrical repulsion of protons. These forces act upon the particles described by the Standard Model, and the particles themselves can be entangled. The world around us, from the simplest hydrogen atom to the most complex biological cell, is built from combinations of these fundamental particles interacting via these forces. But the resulting structures are far more than just the sum of their parts. An atom behaves differently than a collection of unbound quarks and electrons. A molecule has properties utterly distinct from the individual atoms it contains. This is where we begin to see the threads of connection lead to something new, something arising from the complex interplay of the basic elements. This transition from the fundamental building blocks behaving according to the rules of the Standard Model to complex structures with entirely new properties and behaviors is captured by a powerful idea in science, emergence. It in the concept that when simple components interact in large numbers, the resulting system can exhibit characteristics that none of the individual parts possess on their own. It's not just a linear addition. It's a leap to a new level of organization and complexity. Think about water. A single molecule of H0O is just two hydrogen atoms bonded to one oxygen atom. It doesn't inherently have the property of wetness or flow, or the ability to freeze into a solid or boil into a gas. These familiar properties of water emerge from the collective behavior of trillions upon trillions of these molecules interacting with each other through electromagnetic forces described by the Standard Model. The dance of these molecules, their tiny attractions and repulsions, gives rise to the liquid state, to surface tension, to the very notion of wet, or consider temperature. An individual atom doesn't have a temperature. Temperature is an emergent property of a collection of atoms or molecules, reflecting their average kinetic energy, how fast they are moving or vibrating. The concept of hot or cold only makes sense when you have a system of many particles interacting. This principle of emergence is one of the universe's most fascinating tricks. It shows how the simple rules governing the smallest scales can give rise to astonishing complexity at larger scales. Atoms combine to form molecules with unique chemical properties. Molecules assemble into intricate structures like proteins and DNA, and the complex interactions of these biological molecules within a cell lead to life itself, a phenomenon vastly different from the mere collection of its molecular parts. The interconnectedness isn't just about how particles link together. It's also about how these links, in their sheer multitude and dynamic interaction, give birth to entirely new levels of reality, each with its own set of rules and behaviors, from the quantum weirdness at the base, through the emergent properties of chemistry and materials, up to the staggering complexity of biology and perhaps even consciousness. The threads of connection weave ever richer patterns, revealing the universe as a symphony of interconnected layers. While life and consciousness represent astonishing pinnacles of emergent complexity, the universe's interconnectedness delves far deeper, reaching down to the most fundamental scales. Here we encounter a phenomenon that challenges our everyday understanding of reality, one that suggests an inherent, instantaneous link between particles, regardless of the vast distances separating them. This is the realm of quantum entanglement. Imagine two tiny particles, perhaps two electrons, born from the same interaction or specifically paired up. According to the rules of quantum mechanics, these particles can become entangled. Once entangled, their fates are intertwined in a way that defies classical intuition. Measure a property of one particle, say, its spin, which can be thought of as pointing up or down, and instantly, you know the corresponding property of its entangled partner. If you find one electron's spin is up, you know its entangled twin simultaneously, and without any apparent delay, will have its spin down. This happens regardless of how far apart they are, be it a few feet or light years away. There is no signal passing between them at sublight speeds. The information appears to be shared instantaneously. It's a connection that seems to bypass the constraints of space and time as we know them. This spooky action at a distance, as Albert Einstein famously described it, was so unsettling to him and his contemporaries that they questioned the completeness of quantum mechanics itself. But decades of rigorous experiments have repeatedly confirmed its reality. Entanglement is not a theoretical quirk. It is a fundamental feature of the quantum world, a core component of the reality described by the standard model of particle physics. This bizarre link suggests that at the deepest level, the universe might be far more holistically connected than classical physics ever imagined. The threads aren't just about particles touching or interacting through force fields. They can involve these non-local correlations, linking the fundamental constituents of reality in ways we are still struggling to fully comprehend. Quantum entanglement is a powerful, mysterious thread, hinting at profound possibilities and challenging our very notions of separateness and causality in the cosmos. But how do these bizarre fundamental links, the quantum threads described by the standard model and potentially tangled by phenomena like entanglement, weave together to create the vast, intricate universe we see? It's one thing to talk about quarks and leptons, bosons and fields, or particles instantly influencing each other across light years. It's quite another to explain how billions of atoms self-organize into a star, or how molecules combine to form a living cell, or how trillions of neurons generate consciousness and abstract thought. This incredible leap from the simple to the complex, where new patterns, properties, and behaviors arise that weren't present in the individual components, is known as emergence. It's a fundamental principle governing how structure and complexity appear throughout the cosmos. Think of water. A single H2O molecule is just two hydrogen atoms bonded to one oxygen atom. It behaves according to the laws of quantum mechanics and chemistry, but gather billions of these molecules together, cool them down, and something entirely new appears. Wetness, fluidity, surface tension, the ability to dissolve salts and form intricate crystalline ice structures. None of these properties exist in a single molecule. They emerge from the collective interactions of vast numbers, or consider a flock of birds. No single bird knows the grand pattern the flock makes in the sky. Yet through simple rules of interaction with their immediate mates, stay close, match speed, avoid collisions, the entire flock moves as a single fluid and stunningly coordinated entity. The complex flock behavior emerges from simple individual actions. The universe, in a sense, is a grand symphony of emergence. From the fundamental particles obeying the rules of the standard model, chemistry emerges. From chemistry, complex molecules form. From these, in specific environments, under specific conditions, the astonishing phenomenon of life emerges. And within life, particularly in complex biological systems like brains, consciousness and subjective experience arise. The cosmic threads we speak of, the interconnectedness of everything, aren't solely about the direct forces between particles or the mysterious correlations of entanglement. They are also the intricate patterns woven through these layers of emergence, building structure upon structure, scale upon scale, from the quantum foam to the subatomic particles, atoms to molecules, molecules to cells, cells to organisms, dust clouds to stars, stars to galaxies, galaxies to cosmic webs. Each level reveals new, unexpected properties and forms of organization that could not have been predicted by looking only at the level below. Understanding the universe, therefore, requires appreciating not just the fundamental building blocks and their interactions, but also the profound ways in which complexity self-organizes and new properties emerge at different scales. It's a hierarchical structure, where the rules governing one level might be distinct from the rules governing the next, even though they are ultimately rooted in the underlying reality. This intricate dance of emergence, layering simple rules into breathtaking complexity, is a key part of the cosmic tapestry, a process of self-creation and organization that scientists continue to explore, revealing how seemingly simple origins can lead to such profound and intricate realities. And as we explore this intricate dance of emergence, layering simple rules into breathtaking complexity, we naturally ask, what are those fundamental rules, those most basic building blocks from which everything else arises? If emergence is the way structure and function self-organize across scales, what is the most fundamental scale upon which this whole process is built? Scientists have spent centuries probing the very heart of matter and energy, trying to identify the ultimate constituents of the universe. Our current best answer is embodied in a theoretical framework known as the Standard Model of particle physics. Think of it as our universe's fundamental alphabet and grammar, describing the tiny, seemingly indivisible particles that make up everything we see, feel, and interact with, and the forces that govern how they behave. It's a remarkably successful model, tested by countless experiments, from particle colliders smashing atoms together at nearly the speed of light to observations of the cosmos. Within the Standard Model are families of particles, the quarks, which make up protons and neutrons, and thus atomic nuclei, the leptons, like the electron we're all familiar with, and the elusive neutrinos, and the force carrier particles, the photons responsible for light and electromagnetism, the gluons that bind quarks together within protons and neutrons, and the W and Z bosons involved in radioactive decay. Finally, here is the Higgs boson, the particle associated with the field that gives other particles their mass. These particles, interacting through the forces described by the Standard Model, are the foundational threads of the cosmic tapestry. They are the invisible components that determine everything from the structure of an atom to the way stars burn. Chemistry, for instance, is fundamentally a story of how electrons, leptons, interact with atomic nuclei, made of quarks bound by gluons, and the strong force, via the electromagnetic force, carried by photons. Biology, in turn, is built upon the complex chemistry of organic molecules. So, the emergence of life itself, with all its astonishing complexity and diverse forms, is ultimately rooted in the precise interactions dictated by these fundamental particles and forces. The Standard Model, while not a complete picture, gravity remains a challenge to fully integrate, for example, provides a profound insight into the interconnectedness of reality at its most fundamental level. It shows us that, despite the vast diversity of the universe, everything is built from a surprisingly small set of basic ingredients, following a defined set of rules. It is the bedrock upon which the emergent complexity we discussed earlier is built, a universal foundation of fundamental particles and forces weaving together the very fabric of existence. While the Standard Model lays out the particles and forces that act as the universe's fundamental building blocks, describing how things generally interact in a local wet, influence propagating through space at a finite speed, the quantum world that operates within holds even deeper, stranger secrets about interconnectedness step into this realm, and the rules our classical minds understand begin to bend, sometimes break. Among the most perplexing phenomena is one that even baffled Albert Einstein himself, prompting him to call it spooky action at a distance. It's known as quantum entanglement. Imagine two particles, perhaps electrons or photons, created together or interacting in a specific correlated way. According to quantum mechanics, they can become linked, entangled. This isn't like tying two objects together with a string. The connection is far more profound and mysterious. Once entangled, they share a single, unified quantum state, no matter how far apart they travel. The true strangeness arises when you measure a property of one entangled part, say its spin or polarization. At the very instant you determine the state of one particle, the state of its entangled partner is instantaneously determined as well, regardless of the vast distance separating them. Kilometers, continents, light years distance doesn't appear to matter. There is no discernible signal that travels between them. The correlation is immediate. This non-local connection stands in stark contrast to the forces described by the Standard Model, which all operate locally and are limited by the speed of light. Entanglement suggests a level of interconnectedness that exists outside of, or perhaps underneath, the familiar framework of space and time as we usually perceive them. It implies that seemingly separate entities, born from a shared moment, remain fundamentally linked by an unseen thread woven into the very fabric of reality. This phenomenon isn't just a theoretical quirk. It's been repeatedly demonstrated in laboratories around the world, forcing us to confront a universe where the connections are not always visible or even explicable by simple cause and effect across space and time. It reveals a universe where at the deepest level, separation might be more of an illusion than a fundamental truth, hinting at a universe more profoundly connected than we could ever have imagined. This unsettling possibility that particles light years apart can share an instantaneous destiny ripples through our understanding of physics, forcing us to question the very nature of distance and causality. If the universe is woven together at its most fundamental level by these invisible threads of entanglement, what does that imply for the larger structures we see around us? From the dance of atoms within a molecule to the intricate scaffolding of galaxies, everything is ultimately built from these elementary components, governed by quantum rules. But how do the strange probabilistic behaviors of the quantum realm scale up to the predictable deterministic world of our everyday experience? This is where the concept of emergence steps onto the stage, revealing how complex patterns and properties arise from simpler interactions, and how collective behavior can transcend the properties of individual parts. Think of water. A single H0O molecule behaves very differently than a billion molecules together. Individually, they don't have wetness or flow in the macroscopic sense. These familiar properties emerge from the collective interactions of vast numbers of molecules. Similarly, the intricate patterns of weather systems emerge from the interactions of countless air and water molecules governed by physical laws. Life itself is a profound example of emerged complex biological systems capable of self-replication, adaptation, and conscious thought arising from the organized interactions of non-living chemistry. Consciousness, too, the very awareness we possess, is thought by many to be an emergent property of the incredibly complex network of neurons in our brains, none of which are individually conscious. So, while quantum entanglement suggests a fundamental interconnectedness at the universe's deepest roots, Emergence shows us how this foundation of interconnected parts can give rise to breathtaking complexity and entirely new properties at higher levels of organization. The universe isn't just a collection of isolated pieces. It's a dynamic system where connections at one level enable entirely new phenomena at the next, from the fleeting quantum link between two particles to the chemical bonds forming molecules, to the biological processes within a cell, and the gravitational pull binding stars into galaxies. The cosmic threads are constantly weaving, creating the intricate tapestry of reality we observe. Understanding emergence provides a powerful lens through which to view the universe, bridging the gaps between physics, chemistry, and biology. It shows that the laws governing individual components aren't always sufficient to predict the behavior of the whole. New laws, new phenomena emerge from the collective. It's a testament to the power of interaction and organizing, how simple rules applied across vast numbers of elements can spontaneously generate astonishing complexity. This principle bears the interconnectedness not just of particles or objects, but of the very scientific disciplines we use to study them. Physics lays the groundwork, chemistry builds upon it with molecular interactions, and biology witnesses the most complex emergent phenomena of all life itself. It's a cascade of complexity, each level built upon the connections of the one below, reinforcing the idea that the universe is a deeply interwoven whole, from the smallest quantum fluctuation to the grandest cosmic structure. This cascade of complexity, where simpler interactions give rise to more intricate patterns, isn't limited to the emergence of life from chemistry. It's a principle woven throughout the cosmos, from the fundamental particles that make up matter to the vast structures of galaxies. To truly understand the universe's interconnectedness, we must look to its most basic building blocks and the rules that govern their interactions. This is the realm of fundamental physics, the bedrock upon which all other levels of complexity are built. Our current understanding of these foundational elements is captured by what physicists call the Standard Model. Think of it as the universe's alphabet and its basic grammar. The alphabet consists of fundamental parts, the electrons, quarks, and neutrinos that are the ultimate constituents of matter, along with their antimatter counterparts. The grammar lies in the fundamental forces through which these particles interact: the electromagnetic force, which binds atoms together and governs light; the strong nuclear force, which holds atomic nuclei together; and the weak nuclear force, responsible for certain types of radioactive decay. The Standard Model has been incredibly successful, predicting the existence of particles later found in experiments. Like the Higgs boson, it explains the interactions between all known elementary particles and forces, except gravity, which remains a separate puzzle. But even within this framework, the interconnectedness is profound. Every atom in your body, every star in the sky, every cloud in the atmosphere, they are all constructed from combinations of these same fundamental particles, interacting via these same fundamental forces. There isn't one set of rules for us and another for distant galaxies. The language of physics is universal. Yet the Standard Model, for all its power, isn't the final word. It leaves many questions unanswered. What is dark matter and dark energy? Why do particles have the masses they do? How does gravity fit into this quantum picture? These unanswered questions are like missing threads in our cosmic tapestry, hinting at deeper, perhaps even more fundamental connections waiting to be discovered. They push scientists to explore realms beyond our current understanding, seeking a more complete picture of how everything truly links together. The universe, as described by the Standard Model, is a finely woven tapestry of particles and forces. Yet, when we step back to gaze at the cosmos on its grandest scales, a startling realization emerges: the visible universe, everything we can see and interact with, using the Standard Model stucate, the atoms, the light, the forces holding them together, accounts for only about 5% of the total picture. The rest, a staggering 95%, is composed of enigmatic entities we've dubbed dark matter and dark energy. We infer their existence not by seeing them directly, but by witnessing their gravitational fingerprints on the fabric of space-time. Galaxies spin faster than they should based on their visible matter. Clusters of galaxies hold together against their own expansion, and the very expansion of the universe seems to be accelerating. These cosmic behaviors act like gravitational whispers and pushes, telling us that something substantial, something invisible to our current instruments and not included in the Standard Model, is profoundly at play. This reliance on gravity to detect the universe's dominant components highlights one of the deepest challenges in modern physics, incorporating gravity itself into the quantum description provided by the Standard Model. While the Standard Model masterfully describes the strong, weak, and electromagnetic forces governing the quantum world, gravity, the force that shapes planets, stars, and galaxies, remains stubbornly outside its framework. It's described by Einstein's general relativity, a theory of space-time curvature, which works beautifully on large scales, but breaks down in the extreme quantum realm, like the heart of a black hole or the moment of the Big Bang. Bridging this divide, finding a way to weave gravity into the same quantum language as the other forces, or understanding the true nature of dark matter and dark enders, is arguably the holy grail of modern physics. It's a pursuit that requires pushing experiments to unprecedented energies, building vast observatories to peer into the universe's earliest moments, and developing bold new theoretical ideas that venture beyond our current, successful but incomplete models. This quest is not just about filling in blanks, it's about understanding the fundamental rules by which the cosmos operates, from the smallest quantum fluctuation to the largest cosmic structure, revealing ever more profound layers of interconnectedness waiting to be discovered. The quest to understand dark energy pushes the boundaries of what we thought we knew, forcing us to confront the limitations of even our most successful frameworks. For decades, the standard model of particle physics has served as our triumphant guide to the microscopic realm, describing the fundamental particles, quarks, leptons, force carriers like photons and gluons, and three of the four fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. It's an incredibly precise model, confirmed by countless experiments, including the discovery of the Higgs boson. Yet for all its power, the standard model is profoundly incomplete. It doesn't include gravity, the force that shapes the cosmos on its grandest scales, and crucially, it offers no explanation for dark matter or dark energy, which together constitute 95% of the universe's energy content. This stark omission reveals a critical gap in our understanding, a chasm between the quantum world of the very small, where strange rules like quantum entanglement dictate reality, and the cosmic arena governed by gravity, the domain of Einstein's general relativity. Quantum entanglement itself remains one of the universe's most puzzling phenomena, a non-local connection, where measuring the state of one particle instantaneously influences the state of another, regardless of the distance separating them. How does this instantaneous linkage, so fundamental to the quantum realm, reconcile with a universe where the speed of light is the ultimate cosmic speed limit? This question, like the mysteries of dark energy, points towards physics beyond our current grasp. Bridging this divide between the quantum and the cosmic is one of science's greatest challenges. It's a pursuit that fascinated brilliant minds like Stephen Hawking, whose work on black holes and the origin of the universe explored the extreme boundaries where quantum mechanics and gravity both play critical roles. His insights into Hawking radiation, for instance, suggested a deep connection between the quantum vacuum near a black hole's event horizon and the classical gravitational field, hinting at the necessity of a unified theory. Understanding these extreme environments, from the heart of a black hole to the very first moments of the Big Bang, is essential for weaving together the cosmic threads. Ultimately, from the fundamental particles described by the standard model, subject to entanglement's weird rules, interacting via forces both known and unknown, arises the staggering complexity of the cosmos. This process of emergence, where intricate patterns and properties surface from simpler components and interactions, is not confined to life or consciousness. It's fundamental to the universe itself, the vast cosmic web of galaxies, the formation of stars and planets, even the enigmatic push of dark energy shaping the universe's expanse. These are all emergent phenomena, rooted in the fundamental physics, playing out at scales we are still striving to fully comprehend, constantly revealing deeper layers of interconnectedness. These fundamental physics, the very rules governing the universe at its deepest levels, are the bedrock upon which all this complexity, this astounding process of emergence, is built. Our best current map of these ultimate building blocks and the forces acting between them is known as the Standard Model of Particle Physics. It is an elegant, if incomplete, framework that describes the elementary particles we know: CERNs, the quarks that make up protons and neutrons, the leptons like electrons and neutrinos, and the bosons that carry forces like electromagnetism. The Standard Model has been incredibly successful at predicting the results of experiments, confirming the existence of previously theoretical particles like the Higgs boson, which gives other particles mass. Yet even within this elegant model, and certainly beyond it, lie phenomena that stretch our understanding of reality, revealing connections far stranger than those we encounter in our everyday lives. One such profound mystery resides within the quantum realm described by the Standard Model. Quantum entanglement. Imagine taking two particles, perhaps two electrons or two photons, and linking them in a specific way. According to quantum mechanics, these two particles can become entangled, their fates intertwined regardless of the distance separating them. If you then measure a property of one particle, say, its spin or polarization, you instantly know the corresponding property of the other entangled particle, even if it's light years away. It's as if they share a hidden thread connecting them across the vastness of space, a thread that communicates information faster than the speed of light, seemingly defying the limits of relativity. This isn't just theoretical speculation. Quantum entanglement has been repeatedly demonstrated in laboratories around the world. It's a bizarre, non-local connection that challenges our classical intuition about cause and effect and locality. It suggests that at the most fundamental level, The universe isn't just made of independent pieces interacting locally. Here is an inherent, deep-seated interconnectedness woven into the fabric of reality itself. These entangled links are part of the substrate from which everything emerges, a constant reminder that the cosmos holds wonders and connections we are only just beginning to grasp. If quantum entanglement suggests this deep-seated interconnectedness woven into the fabric of reality itself, a kind of fundamental substrate, the question then becomes, how do we get the astonishing complexity we see all around us? How does this bizarre, interconnected quantum realm build towering galaxies, intricate ecosystems, or conscious minds? The answer lies in a concept called emergence. Emergence is the process where complex patterns, structures, and properties arise from simpler interactions. Think of water. A single H0 molecule isn't wet. Wetness is a property that emerges only when billions upon billions of these molecules interact collectively in a liquid state. The rules governing individual molecules are simple, but their collective behavior creates something entirely new: fluidity, surface tension, the ability to dissolve substances. The universe, from this perspective, is a grand tapestry woven by emergence. The fundamental particles described by the Standard Model and the forces that govern their interactions, electromagnetism, the strong and weak nuclear forbans, provide the building blocks and the rules. But these fundamental rules on their own don't explicitly contain instructions for how a snowflake forms, how a star ignites, or how a brain generates. These higher-level phenomena emerge from the vast number of interactions occurring at the simpler levels. It's a hierarchical structure. Potato physics gives us the quarks and electrons and photons. Chemistry emerges from how these particles combine to form atoms and molecules governed by electromagnetic forces. Biology emerges from complex chemical reactions involving intricate molecules like DNA and proteins. And consciousness, perhaps one of the most profound mysteries, emerges from the complex network of biological interactions within a brain. Even the largest structures in the cosmos, the galaxies and galaxy clusters that stretch across the observable universe, are emergent phenomena. They arise from the gravitational interactions of countless particles, organized into stars and gas clouds, following the laws of gravity laid out by Einstein, which themselves might be considered an emergent property of space-time at large scales. This journey from the fundamental, often counterintuitive realm of quantum mechanics and particles to the emergent complexity of our everyday experience was a central theme for many physicists, including the brilliant Stephen Hawking. His work, though focused on the grand scale of the universe, the origins of space-time, the nature of black holes, was always implicitly grappling with how the fundamental rules dictate the structure and evolution of everything we see. He sought the underlying principles, the mind of God, as he famously put it, that governed this incredible process of emergence, turning the simple substrate into the cosmos in all its wonder. Understanding these cosmic threads means understanding not just the fundamental particles, but how their simple dance gives rise to the spectacular, interconnected symphony of reality. To truly trace these cosmic threads, we must venture deep into the heart of matter itself. We must explore the realm governed not by the gravity that shapes galaxies, but by the strange, counterintuitive rules of the quantum world. This is the domain described by what physicists call the Standard Model, our current best map of the fundamental particles and the forces that act between them. Think of the Standard Model as the universe's basic alphabet, its fundamental building blocks. It's a collection of quarks, leptons, like electrons, and force-carrying particles, like photons, all interacting through four fundamental forces: electromagnetism, the strong nuclear force, the weak nuclear force, and gravity, though gravity isn't fully integrated into the Standard Model yet. It's a sort of cosmic particle zoo, each inhabitant with its own peculiar properties, obeying strict mathematical rules. And within this quantum realm lies one of the most perplexing yet profound connections of all: quantum entanglement. Imagine two particles, perhaps born together or having interacted in a specific way, becoming inseparably linked, no matter how far apart they are. Measure a property of one particle, say its spin, and you instantly know the corresponding property of the other. even if it's light years away. D. Here is no signal traveling between them. The link is instantaneous, defying our everyday understanding of space and time. It's what Einstein famously called spooky action at a distance, and it hints at a deeper, non-local interconnectedness woven into the very fabric of reality, suggesting that at the deepest level, everything might be more connected than we can easily grasp. These seemingly simple particles, obeying these strange rules and capable of bizarre links like entanglement, are the ultimate source material. Their interactions, governed by the forces of the Standard Model, provide the foundation from which everything else emerges, from quarks binding together to form protons and neutrons, to these nucleons forming atoms, atoms forming molecules, and molecules arranging themselves into the incredible complexity of biological systems, or the vast structures of stars and galaxies, all stems from this fundamental dance. The emergence that captivated minds like Stephen Hawking isn't magic. It's the intricate, cumulative result of these basic pieces interacting according to their fundamental instructions. Understanding these instructions, laid out by models like the Standard Model and revealed by phenomena like entanglement, is key to understanding the symphony of reality, not just the notes, but the rules of harmony that create the whole. The challenge and the wonder lies in seeing how these fundamental rules of harmony are applied across the immense canvas of the cosmos. If the universe has a score, frameworks like the Standard Model are attempting to write it down, detailing the fundamental parts, the quarks, leptons, and bosons, and the forces that govern their interactions. These are the most basic components we currently understand, the irreducible building blocks that participate in the universal dance. But knowing the dancers and their basic steps isn't enough. The magic lies in how they interact, how billions upon billions of these fundamental particles, influenced by the forces and obeying the strange dictates of quantum mechanics, including that spooky action at a distance, quantum entanglements, arrange themselves, connect, and influence each other. It's through these relentless myriad interactions that complexity isn't just possible, but seemingly inevitable. Consider the humble atom. It's not a solid miniature solar system, but a buzzing cloud of probabilities, governed by the strong nuclear force binding the nucleus and the electromagnetic force holding the electrons in their orbitals. These forces, described within the Standard Model, dictate how atoms form, how they bond with other atoms. Simple rules, yes, but applied across trillions of particles, they give rise to molecules. Water, sugar, proteins, each with properties vastly different from the atoms they are made of. This is emergence in action, chemistry arising from physics. Then comes biology emerging from complex chemistry. Life, in its astonishing diversity, is a monumental example of emergence. The intricate dance of molecules within a cell, the coordinated action of cells forming tissues, organs, and ultimately conscious beings, are all layers of emergent complexity built upon the foundation of physics and chemistry. Stephen Hawking often pondered the deep questions about the universe's origins and fundamental laws, always aware that the most profound phenomena, including our own existence and consciousness, spring from these deepest roots. It's a dynamic system where the parts are constantly in dialogue, their interactions weaving the intricate tapestry of reality, from the entangled fate of distant particles to the formation of conscious thought in a human brain. It is this relentless, rule-bound interaction that builds the world we see, touch, and think about. Understanding the rules is crucial, but seeing how they orchestrate the symphony is the true marvel. To grasp how the universe weaves this reality, we must first understand the fundamental threads themselves and the elementary forces that manipulate them. Our current best model, the most precise and tested theory we have for describing the smallest constituents of matter and their interactions, is known as the Standard Model of particle physics. Think of it as the universe's alphabet and basic grammar. The Standard Model lays out a surprisingly short list of fundamental particles divided into two main families: fermions, which are the matter particles that make up everything we see, and bosons, which are the force-carrying particles that mediate interactions between fermions. Among the fermions are the quarks, which combine to form protons and neutrons, the building blocks of atomic neutron and leptons, like the familiar electron and its ethereal siblings, the neutrinos. These tiny, irreducible entities don't just exist in isolation. They are constantly interacting, pushed and pulled by fundamental forces. The Standard Model describes 3 of the 4 known fundamental forces: the electromagnetic force responsible for holding atoms together and all chemical reactions, the strong nuclear force, which glues quarks together inside protons and neutrons and holds the nucleus itself stable, and the weak nuclear force involved in radioactive decay and crucial processes like those powering the sun. These forces are mediated by messenger particles, the bosons. Photons carry the electromagnetic force, gluons the strong force, and W and Z, bosons, the weak force. And overseeing it all, providing mass to many of these particles, is the Higgs boson, associated with the pervasive Higgs field. It is the countless, relentless interactions between these fundamental particles, governed by the precise rules encoded in the Standard Model and quantum mechanics, that give rise to the complexity we observe. Quarks and gluons form protons and neutrons. Protons, neutrons, and electrons, bound by the electromagnetic force, form atoms. Atoms interacting electromagnetically form molecules. Molecules, in vast, intricate arrangements, form cells. Cells form tissues, organs, organisms. From the elegant simplicity of the Standard Model's particles and forces emerges the staggering diversity and complexity of the cosmos, including the emergence of life itself, a profound example of complexity arising from simpler parts. This framework, however, isn't the final word. It doesn't fully incorporate gravity, the 4th fundamental force, and it remains silent on the mysteries of dark matter and dark energy which dominate the cosmic landscape. But, as our most successful map of the micro-world, the Standard Model is a crucial piece of the cosmic tapestry, revealing how the universe's most basic interactions build the macroscopic world we inhabit. Yet, even with the Standard Model's remarkable success in describing the fundamental particles and forces at the smallest scales, it leaves a significant gap in our understanding. The force it doesn't include, the one we experience most directly in our everyday lives, is gravity. While Einstein's general relativity provides a stunningly accurate description of gravity as the curvature of space-time on large scale, governing the motion of planets, stars, and galaxies, it breaks down at the quantum level, the very realm where the Standard Model reigns supreme. This disconnect presents one of the greatest challenges in modern physics, the quest to unify gravity with the other fundamental forces described by the Standard Model. It's a search for a single overarching framework, often called a theory of everything, that could describe the universe from its largest structures down to the smallest quantum jitters. The conditions where this unification becomes absolutely essential are also the most extreme and mysterious corners of the cosmos. Think of the singularity at the heart of a black hole, where matter is crushed to infinite density and space-time is stretched beyond comprehension. Or the fleeting instance immediately following the Big Bang, when the entire observable universe was packed into a space smaller than an atom. In these realms, gravity becomes immensely strong. Our current theories give conflicting and incomplete pictures. It's like having 2 incredibly detailed maps, one for the continents and oceans, and one for the intricate street plan of a single city, but no map showing how the city sits within the landscape, or how the smallest alleyways connect to the vast global network. Brilliant minds have grappled with this puzzle for generations. Among them was Stephen Hawking, whose groundbreaking work on black holes dramatically illustrated the places where general relativity and quantum mechanics clash. He showed that black holes aren't just cosmic drains, but quantum objects that can, paradoxically, emit rays now known as Hawking radii, a process that seems to require a quantum understanding of gravity itself. His insights pushed the boundaries of our thinking about these extreme environments and the fundamental nature of space-time and quantum mechanics. The search for this unified theory continues, driven by the hope that understanding the universe's most extreme conditions will unlock the deepest secrets of cosmic threads. The puzzle that Stephen Hawking illuminated, the clash between the smooth fabric of space-time described by gravity and the choppy, unpredictable realm of quantum mechanics, highlights one of the most profound challenges in modern physics. It's the search for a theory of quantum gravity, a framework that can describe both the very large, the universe's structure, and the very small, the behavior of particles, simultaneously, especially in extreme environments like the heart of a black hole or the moment of the Big Bang. Imagine trying to merge two radically different languages into one coherent grammar. General relativity speaks of curvature and geometry, a smooth, continuous reality. Quantum mechanics speaks of probabilities, discrete packets of energy, and bizarre non-locality like quantum entanglement, a fundamentally discontinuous reality at the smallest scales. When you try to apply the principles of one to the domain of the of, like looking at space-time itself with quantum eyes, you run into mathematical contradictions, infinite values, and nonsensical predictions. For decades, physicists have been pursuing various paths toward this elusive, unified theory. Approaches like string theory propose that the fundamental constituents of reality aren't point-like particles, but tiny vibrating strings or membranes, whose different vibrational modes appear to us as different particles and forces. Quantum gravity suggests that space-time itself might be quantized, built from discrete loops, implying a sort of fundamental pixelation of the universe at the smallest scales. These ambitious theories, still very much under development, represent humanity's attempt to find the deepest layer of the cosmic tapestry. If successful, a theory of quantum gravity wouldn't just reconcile black holes and the Big Bang, it could potentially explain the fundamental nature of space and time, resolve the mysteries of dark matter and dark energy, and provide a single, elegant description of all the forces and particles we know, including those described by the Standard Model. The hope is that by understanding gravity at the quantum level, we will uncover the ultimate threads that weave together not just energy and matter, but space-time itself, revealing a universe even more interconnected and strange than we currently imagine. It's a quest that probes the very foundation of existence, driven by the profound intuition that beneath the apparent diversity of phenomena, there lies a deeper unified reality. Where in the vastness of space and time might we hope to find traces of this elusive, unified reality? The quest for a theory that can bridge the gap between the quantum world and gravity, ultimately describing all the fundamental forces as different facets of a single underlying entity, naturally leads us to the most extreme environments the cosmos has to offer. It's in the crucible of immense gravitational pull and staggering energy densities that the deepest secrets of these cosmic threads might be revealed. Consider black holes. These cosmic enigmas represent the ultimate triumph of gravity, crushing matter to unimaginable densities and warping space-time beyond recognition. Yet at their core, near the singularity, physics as we currently understand it breaks down. Here, quantum effects likely become inseparable from gravity, creating a realm where the principles of quantum mechanics and general relativity must intertwine. Understanding what happens inside a black hole, or even at its event horizon, is believed to hold vital clues about quantum gravity and therefore the fundamental nature of reality itself. For decades, brilliant minds have grappled with these puzzles. Among them, Stephen Hawking stood out, pushing the boundaries of our understanding of black holes and the origins of the universe. His groundbreaking work, particularly on black hole evaporation through Hawking radiation, showed that even these seemingly inescapable cosmic traps are not entirely static and can interact with the quantum world. This was a profound demonstration of the interconnectedness of gravity, quantum mechanics, and thermodynamics, hints of the deeper links we seek. Similarly, the moment of the Big Bang itself, the explosion that gave birth to everything we see, was a state of unfathomable density and temperature. All the forces, including gravity, would have been incredibly strong and potentially unified. Probing the physics of that initial instant is another route to discovering the fundamental principles that govern the universe at its most elemental level. It's a journey back to the very beginning, searching for the initial weave of the cosmic fabric. The universe we experience today, with its galaxies, stars, planets, and life, all emerged from that initial state, governed by those same fundamental interconnected laws, the complex arising from the simple, the diverse from the unified. Probing the physics of that initial instant, the moment before inflation swept the universe into vastness and variety, presents immense challenges. We cannot build an experiment that replicates the temperatures and energies present in those first tiny fractions of a second. Our understanding relies heavily on theoretical frameworks, extrapolating the known laws of physics to conditions far beyond our everyday experience. The Standard Model, while incredibly successful at describing the fundamental particles and forces that emerged after this extreme era, starts to break down when we push it back to the very beginning. It doesn't fully integrate gravity with the other fundamental forces, the electromagnetics, strong nuclear and weak nuclear forces. Scientists believe that at those unimaginable temperatures all forces were perhaps unified, acting as a single fundamental interaction. Unifying gravity with quantum mechanics and the other forces into a single coherent theory, often referred to as a theory of everything, or quantum gravitics, remains one of the holy grails of theoretical physics. It's the missing piece needed to truly understand that initial cosmic seed. Figures like Stephen Hawking dedicated much of their work to exploring the universe's extremes, from the origins of the cosmos to the heart of black holes, where gravity dominates and quantum effects become significant. Their insights provide crucial theoretical stepping stones, guiding our search for the deeper principles that governed existence before particles formed, before forces separated, before space and time as we know them solidified. Despite the difficulty in direct observation, the universe itself serves as a powerful, albeit indirect, witness. The cosmic microwave background, radiation, the distribution of galaxies on the largest scales, and the relative abundance of light elements are all echoes of those earliest moments, imprinted with the signatures of the physics that was at play. Studying these large-scale structures and cosmic history is another way we peer back, testing our theoretical models against the grand reality of the cosmos. It reinforces the profound interconnectedness. The tiny fluctuations and fundamental interactions in the nascent universe directly dictated the emergence of everything that follows: stars, galaxies, planets, chemistry, and ultimately, life itself. The most complex phenomena we observe today are, in a very real sense, consequences of the simple, yet powerful, laws that governed the universe at its very beginning. These foundational laws, set in the cosmic crucible of the early universe, are precisely what our current physics models attempt to describe. The Standard Model of particle physics, for instance, represents our most successful framework for understanding the fundamental building blocks of matter and the forces that govern their interactions. It enumerates the cast of subatomic carriers, quarks, leptons, bosons, and the forces that bind them, repel them, or mediate their changes, the strong and weak nuclear forces, and electromagnetism. It's a remarkably accurate description of the universe at its most microscopic level, explaining almost everything we observe in particle accelerators and atomic interactions with incredible precision. But the true wonder lies not just in describing the fundamental, but in understanding how these seemingly simple rules, operating at scales far below the atom, give rise to the breathtaking complexity we see around us. This is the phenomenon of emergence. It's the process by which billions upon billions of atoms, following the rules set by the Standard Model forces, interact to form molecules, which in turn arrange themselves into crystals, liquids, gases, and the fantastically intricate structures of biology. Emergence explains how the fundamental interactions of particles in a star's core produce the light and heat that sustain life on a distant planet, or how the collective behavior of neurons in a brain creates the subjective experience of consciousness. The Standard Model provides the fundamental grammar of the universe, but Emergence describes the rich literature that can be written with that grammar. Consider the forces again: the strong force, keeping atomic nuclei from flying apart; the weak force, responsible for certain types of radioactive decay crucial in stellar processes; electromagnetism, shaping chemistry and light; while gravity remains our great chance, a force shaping the cosmos on its grandest scales, yet stubbornly resisting full integration into the quantum description of the Standard Model. These interactions, operating under the rules we painstakingly uncovered, dictate every physical process, every structure, from the flutter of a butterfly wing to the collapse of a supermassive star. The fact that the same fundamental particles and forces govern the inside of an atom on Earth, the nuclear furnace of our sun, and the exotic conditions around a black hole millions of light years away, there's this profound, universal interconnectedness. It is this astonishing consistency of physical law, from the earliest moments understood through cosmology to the present day described by the Standard Model, that allows us to read the cosmic story, linking the smallest quantum jitter to the largest galactic cluster. It reminds us that the threads are indeed woven through everything. The recognition that these fundamental threads, woven through every scale of the cosmos, isn't merely an abstract concept for physicists. It profoundly impacts how we view ourselves and our place within this grand tapestry, from the peculiar quantum links of entangled particles defying our everyday intuition, yet fundamental to reality's blueprint, to the vast cosmic web of galaxies shaped by gravity. We see the same underlying principles at work. Consider the astonishing phenomenon of emergence, a powerful testament to interconnectedness across different levels of complexity. Simple rules governing atoms and molecules, combined over vast numbers and time scales, give rise to the breathtaking complexity of life itself. Biological systems, with their intricate feedback loops and emergent properties like consciousness, are not separate from physics and chemistry, but rather elaborate expressions of their underlying principles. Life emerges from the dance of molecules, consciousness from the symphony of neurons, all rooted in the fundamental physics described by models like the Standard Model. Pioneers like Stephen Hawking, in exploring the enigmatic boundaries of black holes, sought to reconcile the large-scale structure of gravity with the quantum weirdness of the very small, a quest to understand the ultimate connection points in the universe where these seemingly disparate realms meet. Their work digs the continuous human drive to find the deeper unity underlying the universe's apparent diversity. Our journey through cosmic threads has taken us from the smallest jitter of probability in the quantum foam to the unimaginable scale of the observable universe. At every turn, we found not isolated phenomena, but echoes and resonances across scales, governed by the same underlying logic. This universe is not a collection of disparate parts, but a single, unified system, where every particle, every force, every star, and every living being is, in some way, connected. Understanding these connections is perhaps the most profound journey humanity can undertake. A journey into the heart of reality itself, revealing the intricate, beautiful, and interconnected cosmos we call home. It is a story still being written, woven bit by bit, thread by cosmic thread.